We use chlorofluorocarbons, or CFCs, for all sorts of things: refrigerants, solvents, propellants. But what are they? And how can we explain their unusual properties? Let's do predicted properties. Many uses of CFCs take advantage of them being stable molecules with boiling points that can be varied by changing the number of fluorine and chlorine atoms. Let's consider what influences the boiling points of these molecules. We'll consider what happens when we replace one hydrogen of methane with fluorine and when we replace all 4 hydrogens. We'll do the same for chlorine. A common notation in chemistry is to use X to indicate any halogen, such as fluorine or chlorine. What trends do we predict for the boiling points of these molecules? It is always important to consider each type of intermolecular interaction occurring among the molecules. These molecules are electrically neutral, so there are no ionic forces. However, there may be both polar forces and dispersion forces. We'll consider the dispersion forces first. The strength of dispersion forces is related to the size, or the total number of electrons in the molecule. As we replace hydrogens which have only 1 electron with halogens, we increase the molecular size. The dispersion forces will become stronger and the boiling point will increase. How about polar forces? These are related to the dipole moment. In methane, each CH bond has a small bond dipole, but these cancel each other out due to their arrangement in a tetrahedral geometry, making the molecule nonpolar. When we replace all of the hydrogens with halogens, the bond dipoles still cancel and the molecule remains nonpolar. However, when we replace only one hydrogen with a halogen, the dipoles no longer cancel out, and so the molecule is polar. So based on polar forces alone, we would predict that CH4 and CX4 have similar low boiling points, while CH3X has a higher boiling point. The 2 different types of forces present lead to different rankings. This is not uncommon, and when it occurs, we have to be careful about our predictions. Both forces predict CH4 to have the lowest boiling point, so we can confidently predict that CH4 will have the lowest boiling point. But the ranking of the other 2 depends on which type of force plays the more important role. If dispersion forces are more important, then CX4 will have the larger boiling point, while if polar forces are more important, CH3X will have the larger boiling point. We can look at the experimental data to see which forces play the more important role. For fluorine, we find that polar forces are more important, while for chlorine, we find that dispersion forces are more important. This isn't that surprising when we consider that the sizes of the chlorine atoms, with 17 electrons each, are substantially larger than fluorine atoms, which have only 9 electrons each. Because dispersion forces increase with molecular size, we expect dispersion forces to be stronger for the chlorine compounds than the fluorine compounds. When estimating the strength of intermolecular forces, it is important to consider each type of force present. If the different types lead to different rankings, we have to be careful about making a definitive prediction. Only when all of the forces present lead to the same ordering for a property, such as boiling point, can we be confident in our predictions. And if there is one thing I have learned in life, is that we should all aim to be confident in our facts before we make any bold predictions.